Okay, Sebastian, thanks to the organizers for inviting me here. In the following minutes, I will be talking about Rydberg atoms, and in particular, I would like to present you our approach to engineer spin Hamiltonians using two-dimensional arrays of Rydberg atoms. This work has been done in Palaiseau in the group of Antoine Progress. And for those of you who don't know the group, this is a picture of the team working there. You may recognize Antoine and Cedric, who are the permanent members of the team. And in yellow, you see all the people that are involved in the experiments with Rydberg atoms. Then, on the theoretical side, we have had different collaborations along the years, but mainly for the results that I will show you today, we have the help of the group of Magnetism in Harvard, Mike Saletter in Berkeley, Andreas Rossi now in Lausanne, and more recently, Thomas Russell in India. And I don't want to let this opportunity pass without advertising that there are currently PhD and postdoc positions in the group, so in case you are interested, just contact us. Okay. Then, as for the motivation for our work, I would say that this is a shared motivation with most of you, because we believe that quantum simulation can help us understand the physics behind complex many-body systems. Like, for example, quantum magnets, high-temperature superconductors. There are also problems in high-energy physics or in cosmology, or even transport in molecular wires, or even in biological systems. All these systems that you see here, they have something in common, and is that as far as we can tell, they can be described by simple models, like, for example, the ice, the XY, the Heisenberg, or the Hamiltonians. And in particular, for the platform that I will show you today, the natural Hamiltonians to implement are the IC and the XY. And as for the open question that we are interested in, I would say that we are interested in phase diagrams, the dynamics, which is always difficult to compute for more than 50 particles or so, also topology, the role of disorder and entanglement, this type of many-body systems. And for that, you know that there are many different platforms around that can implement this or some other Hamiltonians. We can have, as we have seen, trapped ions, Rydberg atoms, as we will see in this talk, but also superconducting qubits, ultra-cold atoms, polar molecules, polar condensates, and in general, many others. So what is our platform about? So in our platform, we create assembly arrays of individual atoms. In order to do this, we are using just a dipole trapping that we focus very tightly using two spherical lenses that we put inside the vacuum chamber. And with this, we can create trapped depths for single atoms of around 1 millikelvin with wastes of around 1 micron. So this means that we can trap single atoms in this type of arrays. And in the last years, we have managed to solve some natural problem that we had, that was that the loading of these arrays was not deterministic, and just together with other groups, we implemented techniques to move the atoms around to be able to create different arrays, as the ones that you see here in 1 dimension, 2 dimension. In 3 dimension, we also managed to apply similar techniques to create different arrays as well. All right. And something important that I want to mention is that this technique allows us to create really arbitrary geometries, as you can see in this pixelized version of this well-known picture. All right. Then, as we are in the session of scaling up quantum simulators, some of the limitations that we had initially in our experiment was that the lifetime of the atoms in this type of traps is limited by vacuum conditions. It's around 20 to 25 seconds in atom temperature in our laboratory. And to overcome this problem, we decided to build a new machine where we place basically the atoms in a cryogenic environment. And with this, we managed to extend the lifetime to 6,000 seconds or even more. So that it means that now we can create assemble arrays containing more than 300 atoms with more than 30% probability, as you see in this example. All right. So I showed you that we can create these different free arrays where atoms are typically separated by distances of a few micrometers, like the one that you see here. That means that, in principle, these sites are addressable with laser beams that you can focus without crosstalks and so on. But now, if you want to implement, to be able to study many-body systems, you need interactions, and if you have atoms in the wrong state, atoms just don't interact. And there is where Rydberg atoms come into play. Rydberg atoms are just highly excited electronic states of atoms that have Typically, things you have quantum numbers around 50 to 100 in the lab, and that have very nice properties for quantum simulation. I don't want to go into the details, but basically, there are two very nice properties for quantum simulation: is that they have large anti-dipole moments and also relatively long lifetimes. And the consequence of this is that the interactions between Rydberg atoms are very strong, and this precisely allows for the quantum simulation of complex and memory systems, for example, from condensed matter, on a very different and also more convenient length scale and time scale. Because we see now that for distances of a few micrometers, one can get interaction energies of a few megahertz, which means that the interaction dynamics happen on the microsecond time scale, which is still shorter than the lifetime of Rydberg states of around 100 microseconds. Alright, so then as for the interactions between Rydberg atoms, there are different types of interactions. Perhaps the most well-known interaction are van der Waals interactions that scale as a distance as 1/6. And this happens whenever you have two atoms in the same Rydberg state. And this amounts to a diagonal terms in the coupling matrix that you can use to implement the quantumizing model, where you see the sigma set Pauli operator. But however, there is a second type of interaction that happens whenever you have two atoms in two different Rydberg states that have a different parity. And in this case, the scaling of the interaction is as 1/cube. And you can use this interaction to implement the XY model, where you see this flip-flop type of terms in the Hamilton. So for now, I'm going to speak only in this talk about resonant dipole interactions, and we are going to forget about van der Waals interactions. Okay? So what does it mean? This means that the first step of these experiments is to bring first the atoms to the Rydberg states using light fields, lasers, and then once we are in the Rydberg manifold, we can manipulate the internal states of the atoms just using microwaves, and we can drive coherent Rabi oscillations between these two states, as you see here. And then the effect of the interactions, these type of interactions, is to exchange the internal states of these atoms. If you prepare, for example, one of the states in S and the other one is in P, the effect of the interaction is to exchange the internal state. The atom that was in S goes to P, while at the same time, the atom that was in P goes to S. And this is something that you can measure in the lab, where you can see that for two atoms, you can record these spin exchange oscillations. And now, if you measure the frequency of these oscillations, you can basically measure directly the interaction energy. And this, as I was saying before, allows you to implement the XY model. Alright, so after this short introduction, I'm going to describe you the outline of the remaining part of the talk. I will try to walk you through three different examples of experiments that we have done very recently. In the first part, I will show you how one can prepare dipolar XY magnets, antiferromagnets, and ferromagnets. Then I will show you that using dipolar interactions in the spin XY model, one can get scalable spin squeezing. And then finally, I would like to flash you some recent results that we are just obtaining in the lab, where we try to measure the dispersion relation of particle excitations in the XY model. Okay, so let's go to the first part. Just to put you a reference, perhaps something that you will know better, the IC model, when one prepares, for example, the ferromagnets or the antiferromagnets, in this case, the antiferromagnets in the IC model, usually these antiferromagnets are classical ground states of the system at 1/2 billion or 1/3 billion. Okay? And there has been many examples of this type of preparation in the last few years, starting with some experiments in the group of Emmanuel Bloch, or with experiments in the group of Michel Lupin, or even in our group. And now, if you go to the XY model, the situation is a little bit different, because you see that we can have competing order along X and Y, as you see there. And now, if you ask, how does this ferromagnet or antiferromagnet look like, it's very difficult, because it's not possible to obtain an analytical expression to describe this round state. But you can visualize it in this pictorial way, where basically you can see that the ferromagnet is the coherent superposition of the classical ferromagnets, where you have basically arrows pointing in all directions in the XY plane. And importantly, this ground state at 1/2 billion is a non-classical matter state. Okay, so this is the difference between the two models, or one of the differences. Okay, so this is interesting also because there are many platforms that can implement this type of XY model. But importantly, we have dipolar interactions, means that it's not the interactions that stay more than first neighbors. And we have this platform, for example, polar molecules or magnetic atoms that can implement the same type of Hamiltonian. And interestingly, this in the case, for example, of antiferromagnets, this introduces some degree of frustration. Because you see that if you just take a square and you want to satisfy this antiferromagnetic coupling, you can do it horizontally and vertically, but not along the diagonal. Okay? So this means that, well, along the diagonal, the interaction energy is smaller, but nonetheless, this induces some degree of frustration that changes the properties of the ground states. And in particular, what we expect is that if we are t equals 0, we expect long-range order for both the ferromagnet and the antiferromagnet. But if we are at finite temperature, we only expect long-range order in the case of the ferromagnet. Because for the antiferromagnet, this frustration destabilizes the order, basically. Okay. So we are going to try to prepare this experiment in the lab. So what we're going to do is that we start with this Hamiltonian, which is the natural Hamiltonian in our platform, and we are going to add an extra term, which is a staggered B field along Z. And we are going to do that in order to prepare a classical Nell state along Z in this type of checkerboard pattern, as you see here. Okay. So what we are going to do is to apply some local light shifts, some beams that will focus very tightly in the positions of the sublattice beam, as you see here, using a second SLM that we have. And then, when you do this, what you can do is you can apply microwaves to flip the spins that are not addressed by these adhesive beams. And with this, you start in this classical state. And now, the interesting thing is that when you start from this configuration, the configuration is symmetric and you can prepare both the ferromagnet and the antiferromagnet. Because now, if you look at this value of this delta, which is the value of the detuning of a laser and resonation, and you start with negative values of delta, and you decrease adiabatically the strength of this staggered field, then you can prepare the antiferromagnet. But if you start with positive values of delta, and you do the same, then you prepare the ferromagnet. So you see that basically, in the same experiment, by just changing the sign of the detuning of your laser, then you can access basically the preparation of both the ferromagnets and the antiferromagnets. Alright, so this is the experiment, this is this spinning lattice, this is the value of the light shift that you see here. And what we're going to do is to decrease adiabatically this spinning lattice. And finally, we basically do a pi/2 rotation and we read the results in the X basis. And we do this for 100 atoms. And if you wait around 1 microsecond, this is the type of correlation that you obtain in the case of the ferromagnet, where you see that everything is well, is positive correlations everywhere, as expected for the ferromagnet. And you can have this staggered configuration in the case of the antiferromagnet. And now, if you just evaluate these correlations, how the correlations evolve as a function of the distance, what you see is that if you plot it in a 1D plot, in the case of the antiferromagnet, these correlations quickly decay to 0. But in the case of the ferromagnet, even for the longest distances that we can measure, this value saturates at a finite value. Okay, so this means that we can see long-range order in the case of the ferromagnet. And the antiferromagnet is destabilized by imperfections in our system. Okay? And this points out to the role of the tail of this dipolar interaction in the preparation of the ferromagnet and the antiferromagnet. And I want to mention also that after we published these results, there has been some controversy that says that probably this is not an equilibrium situation, but nonetheless it's very interesting because this means that the things that we are doing in the lab is of interest for many other groups. And in particular, there has been also some recent experiments in the group of Chris Monroe, where they have obtained also similar results for the case of 1D chains. All right. So with this, we are going to go to the second part. In the second part, what we wanted to see is that if one can use this model to engineer or to create spin squeezing with dipolar interactions. And for this, we are going to start with the most simple protocol that one can imagine, which is let's try to prepare a coherent spin state along Y. This is the state that we are going to prepare. This state has associated quantum projection noise in the X set plane, as you see here, which is symmetric. Basically, it has a circular shape. And then what we're going to do is to time evolve this initial state with a Hamiltonian of interest. In our case, it's the XY Hamiltonian, with the hope that we can reshape this quantum projection noise into a different shape to get from a circle into a different ellipse. And finally, we are going to measure the squeezing at a different time. Okay? With the hope that we can improve the field resolution by just reshaping this quantum spin projection. And before continuing with this, perhaps I should mention that the canonical way to create the spin squeezing in other systems is to use the one-axis twisting Hamiltonian, which is described by the expression that you see here, where you have this Pauli sigma set matrices. And this is importantly an all-to-all type of Hamiltonian. And then the idea is, well, the dipolar XY model that we are dealing with, it has approximately the same structure as the one-axis twisting model. Okay? In particular, the two Hamiltonians are the same in the case of infinite range interactions. And then the idea is, well, do we really need an all-to-all connectivity? Is the 1 over r cubed long range enough to generate the spin squeezing? And this is important and it's very relevant because there has been some experiments in many platforms where they have used this one-axis twisting Hamiltonian, in particular, for example, with Bose-Einstein condensates, in cavity QD, with platforms, and even with ions. And this is normally, for most of these platforms, not the natural Hamiltonian to implement these models, so it means that you need to work hard to be able to obtain spin squeezing. If spin squeezing is possible with dipolar interaction, then many other platforms will have access to spin squeezing. And the good news is that yes, the prediction is yes, there have been some papers in the literature time ago, and it was revised very recently by Tommaso Rosete and Nanomaterials. In order to characterize how much squeezing one can get, one usually defines what is called a squeezing parameter, psi squared, as you see here, which is basically the measure of the variance of this magnetization, basically along the shortest path of this ellipse, divided by the total length of the spin, d squared. Okay? And this squeezing parameter can have values from 1, where you have the standard quantum limit, down to 1 over n, that is imposed by the Heisenberg limit. Okay. This is interesting because this squeezing parameter is directly related to the metrological gain that you can get in Ramsey type of experiments, as defined by Dave Weinman in the 90s. And the interesting thing also is that not only you can have a spin squeezing, but it should scale. And when you look at the scaling with the number of particles for this squeezing parameter, and also for the optimal time at which you obtain this spin squeezing, is very similar in the case for the prediction of the XY model. These are simulations done by the group of Tommaso Rosete, where you see that the exponents are approximately the same. So what we're going to do in the lab is to start with this coherent spin state along Y here, and then in order to do this, we apply a pi over 2 microwave pulse. We let the system evolve, as I was mentioning before, and then finally we use an analysis pulse where we can basically rotate this ellipse in the plane and basically measure the squeezing or the magnetization along Z. And when we look at the variance as a function of this angle theta, you see that there is one part of the curve basically that is below the standard quantum limit. So we can get a spin squeezing this type of system. Now what we can do is to repeat the experiment with different times, and then to find an optimal time at which you can get a higher degree of squeezing. And from these two curves, which is the length of the magnetization basically, and the variance of the magnetization, you can infer this spacing parameter, and then you see that you can measure values like 3.5 dB below the standard quantum limit. Okay, and more importantly, I would say that this is something interesting, is that this spin spacing scales with the number of particles. When you change, for example, the system size, as you see here, for both the length of the magnetization and also for the variance, as you see there, and this allows you to basically reconstruct the spacing parameter as a function of the number of particles and also the optimal time. Okay. This is the scale. So we can get a really scalable spin spacing instead of XY model. And this is something that is very timely because basically at the same time that we were doing these experiments, other groups obtained similar results. In particular, in the group of Christian Ross in his group using trapped ions, and also with less Rydberg atoms in the group of Alan Monica Schneider's. Alright, so this was everything for the spin spacing. So far we were only looking at the global observables, but one can have the microscopic details of the rules of the system. Okay. And one initial question that we had is it possible to measure the dispersion relation of quasi-particle excitations in this type of model? And this is also very interesting because in this type of dipolar systems, we have seen that the valence states of the ferro and the antiferromagnet are modified because of the tail of these dipolar interactions. But actually, for the dispersion relation, you also expect a modification. In particular, you see that for the case of the ferromagnets, basically the dependence on the momentum goes from q squared to a square root of q. So this is something that was predicted some time ago by Hans Peter Schler. And this is something that we were interested in measuring in experiments. And in order to do that, what you need to do is to map your spin Hamiltonian to a particle Hamiltonian. And I don't want to go into the details, but basically what this says is that your Hamiltonian in terms of a particle Hamiltonian now has different terms. And in particular, it has a rotor term that is responsible for the dynamics of the spin spacing that I showed you before. And importantly, there is another term that is the spin wave term, which you can basically describe with quasi-particles that are independent, that are developed in this type of system. Okay. Something which is very interesting is that one can define a temporal structure factor that is nothing else but the Fourier transform of the correlations around Z. And this is something very interesting because now if you have access to this structure factor as a function of time, then you have access to the dispersion relation in this system. Okay. So that means that by measuring the dynamics of the correlations, one can obtain this dispersion relation. So what are we going to do is the same experiments as I showed you before. So basically we start with all the atoms in the state for the ferromagnet. Remember that this is not the absolute one state, it's just one of the states in the Rydberg manifold. We apply pi/2 rotation, basically, to put the spins around the XY plane. And then we measure the correlations as a function of time, as you see here, where you can see that there are anti-correlations developing. This is as a function of the distance. And now what you do is to Fourier transform these correlations. And this is what you get, where you can see this verse as a function of q, the momentum. That basically you start to see some oscillations that are later very large. But you see that the frequency of these oscillations is changed, at least the initial point in the curve. This is for the ferromagnet. You can do exactly the same thing for the antiferromagnet, as you see there. And now, what you see in comparison with the case of the ferromagnet is that these oscillations are less, are more damped, I would say, and also they are slower. Okay, so this is the results. When you measure, you fit the first part of these oscillations in the case of the ferromagnet, as you see here, and in the case of the antiferromagnet. And what you see is that basically the behavior, again, is very different in the case of the ferro and the antiferromagnet. Which points out, again, the effect of the dipolar interactions. the non-grain state of interaction and in the dispersion relation. Okay. And now you ask me, what about the prediction? Are you able to see something about the prediction? Well, the thing that we can say is that to be able to extract the dependence of the square root of Q for the case of the ferromagnet, the one is to have access to larger sizes, because it's very difficult to access Q equals 0. Moreover, that you can have also imperfections due to the reflection of the spin waves at the boundaries. Okay. But nonetheless, you see that the behavior is very different. And here, I should mention also that you see that this is like noise. But if you compare the results of the experiment in red with the numerical simulations done by Thomas Orosilides, you see that actually this is not noise. And this comes actually from the representation in this type of blood. But nonetheless, I think it's important to say that one needs to basically extract this dependence for a low K. So this is a little bit different. All right. And with this, I'm coming to the end. I hope I could convince you that this platform is a very nice platform where one can engineer synthetic matter. And something that I would like to mention also that is possible. I was saying that we have basically two types of Hamiltonians that we can implement in the platform. But we can extend to other models, like for example the XYZ model, using techniques of blockade engineering, as we have done some time ago in our group. And also we can implement, for example, spin orbit trapping, as you see in the example that we have done also a couple of years ago in the case of 3 atoms. Then, as future directions that we would like to explore in the future are topological matter in 2D, and also we would like to explore exotic phases of matter, like for example spin liquids. And we are also working to the scalability to thousands of the spin, probably also using a cryogenic set. Okay. And this is everything. Thank you very much.
Thank you very much for your wonderful talk. Are there any questions? Yeah.
Sorry. Hi Daniel. Thank you for the wonderful talk. Well, quick question. Is the phase difference between the excitation rate for the spin squeezing experiment, the phase difference between phase relations between the excitation laser and the RF wave, does it play any role in the measurements at all?
The phase of you mean the phase of the laser?
Yeah, you want to map the spin state.
Yes, you can actually in this microwave pulse that you have here, you can vary also the length of this pulse, and you can also vary the phase in order to basically measure correlations. You can measure, for example, correlations in XY in all the directions.
Yes, and you're using traveling wave.
For the microwave, yes. It's a microwave that we put with some antenna in the channel.
Hi, thanks. I was wondering what the limiting decoherence process is in this XY encoding. Is it the dephasing between the two Rydberg states or the decay?
Well, there are some dephasing and some imperfections, critical imperfections that you can have. For example, when you in the case where I was showing you this, for example, for 2 atoms, just I was mentioning that you can record this coherent spin exchange between these, for example. You see that there is a small damping in there. And this damping it has to do with actually the finite temperature of the atoms. You can put the atoms to the absolute vibration at 1 state. But nonetheless, what happens is that in our experiments, Rydberg atoms are not trapped. And in order to do this experiment, we actually do experiments with the optical pieces, and we do the experiments in real time. So this means that the atoms come here. And this leads to actually to this residual temperature that you get. The velocity of the atoms leads to some. Then you can have also some damping, for example, because But mostly electricity is the basic mechanism has to do with the motion of the electron. That it is all those things that have because of the traps that are not recycled in position.
Cool, thanks.
So thank you very much for the talk. That's very interesting. Great.